Swayam Prabha. Digital India. Educated India.
So, in the last lecture, I showed this particular diagram where delta P is plotted against gas flow rate for different liquid flow rates. Okay. So, the outcome of this picture is that it gives a kind of a qualitative dependence of a pressure drop in a packed column when we manipulate the flow rates of gas and liquid. Okay. So, the pressure drop increases when you increase either the gas flow rate or the liquid flow rate. And then we also talked about what happens when the flow rates are very high. Okay. So, when the flow rates gets very high, we have that problem of flooding, and where the entire column is filled with liquid and the gas will bubble through it and the column becomes unstable. So, that is the flooding line here. And a safe operating zone is the zone that is kind of hatched here. Okay. So, this zone is the safe operating place for the packet bed. Okay. So, generally this kind of plots are very useful if you want to calculate delta P for a given gas flow rate, liquid flow rate and diameter of the column. Now, generally these flow rates are specified based on the process requirement. Okay. Recall that this mass transfer operating equipment will be working along with the rest of the other process equipment such as reactors and other mass transfer equipment. So, the flow rates are pretty much specified by the design. Now, for those specified flow rates and the diameter of the column D, you can use these plots to calculate the pressure drop. Okay. Let us say the pressure drop that you get happens to be somewhere here along this line. Okay. Then we know that this is not an operating possibility. So, what we do? We try to change the column diameter so that we can bring the delta P down. We know that because from Ergun equation for a dry packing, that is flow of a single fluid through a packet bed, I showed that the delta P is proportional to the mass velocity squared, or in other words proportional to 1 over a square or 1 over d power 4. So, I can control the pressure drop by choosing a column with a larger diameter. Okay. So, I kind of increase the diameter, and then maybe I may come to another pressure drop level somewhere here, still not good enough. Again I keep decreasing this, I keep increasing this diameter of the column. So, this becomes more like an iterative process. So, you keep changing your diameter and then correspondingly calculate the pressure drop and see if this pressure drop falls in this safe operating zone, right. So, but because this is a very iterative process, it would be probably better if you replot this figure such a way that we have curves for a given pressure drop and then look at the corresponding flow rates. Okay. So, let me explain what this means, what I mean by this. So, let us take this graph and I would like to plot the same information. I am trying to plot in a different way. Let us say I have gas flow rate here and the liquid flow rate here. Okay. So, what I will do, I will try to choose a pressure at this point. So, along this line the pressure drop is constant. Okay. So, let us say I start from here, this point 1, this is where the liquid flow rate is 0, only the gas is flowing. So, that I can mark somewhere here, this is point 1. Now, along the line I move to finite liquid flow rate. Okay. So when I move from 1 to this point 2, what happened is the liquid flow rate has increased, but the gas flow rate has decreased. So I can mark point 2 somewhere here. Okay. So if I go somewhere here, this would actually correspond to another liquid flow rate, and this liquid flow rate at 3 would be smaller than, the liquid flow rate at 3 would be higher than at point 2. So I may have to plot somewhere here. Okay. So at point 3, the gas flow rate has decreased, but the liquid flow rate has increased. So I can actually collect many such points, and then I can draw this. This need not be a line, but this will be a curve. This corresponds to a particular delta P1. Same information, but plotted differently. Why this is useful? Because now if I am interested in this particular pressure drop, I have a range of gas flow rates and liquid flow rates I can choose from, so that the delta P will be constant along this line. Let's take another line. So I want to do the same thing for another pressure. So this is delta P2. Okay. So again I start from this point here. So compared to this point 1, this point, let me call this point as 1 prime. 1 prime is also in the dry packing, but clearly point 1 prime is actually above point 1 in the gas flow rate. So I should be locating 1 prime somewhere here. Again, liquid flow rate is 0, only gas is flowing. So this point 1 prime will be above 1, meaning pressure drop is more. Okay. Clearly this delta P2 is more than delta P1. So this is for delta P1. And then I choose another point somewhere here. So that would be here, 2 prime. And then I keep doing this over and over. So I can collect many such points, and then I make another line. So this is for delta P2, and maybe in another line that will be for delta P3, and so on. So now when I have the plots of this order, then I can easily say what is my design pressure, so that I am not flooding the column. I may say choose a pressure drop corresponding to flooding, or maybe 50% of the flooding pressure, or maybe 80% of the flooding pressure drop. So I can choose a particular line corresponding to that particular design or target pressure drop, and then I can choose different possible combinations of L and G. Okay. So this is not iterative anymore now, because I can, in one go, I can set the pressure drop requirement, I can calculate the desired gas and liquid flow rates or flow velocities. Okay. And this has become very useful in that sense. So what I'm going to show now is, even though this is what we want, but the plots need not be always in this very simple form, L versus G. It will be some combination of L and G. Okay. So let me show you that. So this is for structured packing, this is for random packing. And this plot is for structured packing. So you can clearly see, suppose if you look at this particular figure, you can see this y-axis is not G, but it is some factor called capacity factor. I am going to define this what it is. On the x-axis, it is not just L, but it is some ratios of the flow rates of liquid to gas. Okay. And if you look at these curves, each of these curves corresponds to different pressure drop, and the pressure drops are given in slightly different units. It's given in English units. Okay. And now subsequently what I'm going to do is, I'm going to discuss how to define capacity factor and the corresponding unit systems for each of these given pressure drops. Okay. So the x-axis or the abscissa is given as L double prime over G double prime square root of rho G by rho L. Okay. So this is the x-axis. variable. This L double prime here, this is the liquid mass flux or mass velocity. This should be in the units of lb over feet squared second. In this particular plot, English units are used. Whenever we want to use this particular plot, we have to work with English units. This G double prime here is the gas mass flux or mass velocity. This also is given in the units of pound per square of foot squared second. Rho g, this is the density of gas given in pound per feet cube. Rho L is density of liquid, also in the units of feet. So this group of term is non-dimensional. Yeah, you can use it. Like I said, these plots are actually made in English units. So if you want to, so what you need to do, you basically have to multiply by a conversion factor if you want to use in SI units. That's all. Okay. So these plots are made long time ago. Okay, and this is what industries also use. And like I said in the beginning, you should be adept with changing of units. Okay, between SI to English and vice versa. Okay, so this is one example where, as far as this particular plot is concerned, whenever you want to use this particular plot, you need to use English units. Okay, now let's look at the ordinate or the y-axis. So this capacity factor, in short, I will use Cp, is defined as G double prime F to the power 0.5 nu to the power 0.05 divided by square root of rho g into rho L minus rho g. Okay, this definition is for random packing. So G double prime is gas mass flux, like we discussed here. Okay, this G double prime. This F here is called the packing parameter. F is the packing parameter, and this is given in the units of 1 over feet. Okay, this will be specific for a given packing material. So if you look at this particular table, this gives the F parameter values for different kinds of packing material: ratching ring based on ceramic, metal, burl saddles, pal rings, interlace saddles, high pack rings, so and so. Okay, so on the left hand side you have different kinds of packing material, and then these packing material can come in different sizes. Okay, here the sizes are given in inches, again English units. You can have ½ inch, you can have 1 inch, or the biggest would be something like 3 inch. Okay, so for a given packing material and a given size, the F parameter is given here. Okay, right now don't look at all the values given in the parenthesis. This is not useful right now. Look at only the values given in the non-parenthetic information. Okay, for example, if you want to use a ratching ring of 1 inch, you will see this F parameter. F is 179 1 over foot. Let's say if you want to use interlock saddles of 2 inch and you would read this value to be 40. Okay. So, this F, packing parameter F, depends on the packing material and its size, and that's something you get it from this kind of plot or tables. Okay. So, going back to the definition of capacity factor, G double prime is the gas mass flux, F is the packing parameter dependent on the packing material and size, and nu here is the kinematic viscosity. And this should be given in centipoise. Okay. Each parameter has to have the associated unit system. Okay. You have to use these variables only in these units. If it's given in other units, you have to change it back to these units. Rho G, rho L, we have already defined. Kinematic viscosity of the it will be of the liquid. Okay. This is actually of the liquid. Yes. Okay. Now, another thing we have to be careful about this is, this pressure drop is given in the units of pressure drop per unit length of packing. Okay. This is not the total pressure drop, this is pressure drop per unit length. Why it is given per unit length is because then the dependence on the packing height or packing length is not relevant anymore. Okay. Because it is per foot of packing, so that the total length of the packing is not important. Okay. So, thereby we are actually reducing 1 degrees of freedom here. So, also if you look at the unit, even though it is given as delta P, it should be delta P by L or delta P by Z. This is Z here is the height of the bed. Okay. But here it is given as delta P, so it should be delta P by Z, where Z is the height of the packing. So, what I mean by height of the packing is, if I go back here in this packing, so this entire packing height is a total packing. Okay. The total pressure drop is measured and then divided by the length of this height of this packing, that is the per delta P for 1 foot of packing. Okay. So, that is, so if you look at the unit system for delta P by Z, this is actually given in the units of inches of H2O over 1 feet of packing. Again, when you look at pressure measurement, we use pascals, we use atmosphere, we use bars. Okay, these are the unit system. But sometimes we also say in terms of mmHg. Okay, or mm water. Okay, depending upon the working fluid. So here it is used in terms of inches of H2O. Okay. So, and if you see this, each of these constant pressure drop lines are in this unit, inches of H2O per unit foot of packing, and you can see it starts from 1.5, 1 and so on so. Okay. And experimental observations actually suggest that whenever this delta P by Z is 1 inch of water per feet, that's where flooding happens. Okay. So, the flooding pressure drop is actually 1 inch of H2O over 1 feet of packing. In terms of English units, SI units, this would be about 816.4 Pascal per meter. That's a conversion. Okay. So, when you have a column with a pressure drop of 816.4 Pascal per meter, that's where your column floods. Okay. Generally, you would operate less than this pressure drop, meaning you will have to probably choose a curve below. This is like an upper limit. You may choose something like 0.5 or something in between. Okay. So, that's what I was trying to tell you before, that we will be able to give a target or desired pressure drop and then correspondingly get the diameter of the column. Okay. So far so good. What I am going to do now is, I am going to illustrate this with an example of how to use this information and then decide a column diameter for a given pressure drop, so that this use of this information will become more evident. The first example is deliberately designed as a simple one because all the units are given in the English unit, so you don't have to worry about conversion. Okay, whereas in the second problem, I will pose the problem in SI units, and then we have to convert some of the quantities in English units to get the pressure drop, and then back to SI units. Okay, but in this problem, this is very straightforward. Okay. You can see that this is basically about estimating the tower cross section. So whenever we want to do tower cross section or tower diameter, we have to deal with the pressure drop calculations. So the question goes like this: you are planning to reduce the 2% carbon dioxide in 23 pound per second of a natural gas. So this is basically the mass flow rate of the gas using absorption in an aqueous diethylamine flowing at 40 pound per second. So liquid flow rate is also given, gas flow rate is also given. You want to use either 1.5 inch rashing ring or 1.5 inch pal rings. I am going to do calculation only for the rashing ring, and pal ring you can do it yourself. Okay. When we change the packing material, only thing that will change is the packing factor F. Okay. Otherwise everything else will be the same. In either case, you want to design for a pressure drop of 0.25 inches of H2O per feet. I already said 1 inches of H2O per feet is a flooding situation. Here we are using 1/4 of the flooding situation. So target pressure drop is also given to you, so that foaming is minimized. So foaming is a consequence of flooding. Okay, and instead of saying you don't want to operate under flooding, they say foaming has to be minimized. Under operating conditions, the densities of the gas and liquid are also given in the proper units of pound per feet cube, and then the liquid viscosity is also given in centipoise units, centi-Stokes units. Okay, and then what should be the tower's cross sectional area? Okay, this is the question that we have to discuss. Okay, so let me go back. I think I made a mistake here. This should be actually centi-Stoke. Centipoise is the units of viscosity, but here we are talking about kinematic viscosity, and the units is centi-Stokes. So first thing we will do is we will just note down whatever the information that is given. Okay, so G is the mass flow rate, and this is given as 23 pound per second, and L is the liquid flow rate, given as 40 pound per second. Packing material is rashing ring of size 1.5 inch. Delta P by Z is 0.25 inches of H2O by feet. Rho G is 2.8 lb per feet cube. Rho L is 63 lb over feet cube. So the way we will solve this problem is, first we will calculate the value corresponding to the x-axis here. Okay, and then we know the target pressure, which is 0.25. That is, we are going to choose this particular curve. Once we know what is the x-axis value, let's say it's somewhere here, and then we go vertically to that particular line. Imagine this is a vertical line, okay, and this is supposed to be a vertical line, and then you read the data from here and get the capacity factor. Okay, once you know the capacity factor, from there I will show you how to calculate the diameter. Okay, so that's the strategy. So we want L double prime by G double prime square root of rho G over rho L. But we don't know L double prime. L double prime is what? This is a liquid mass velocity. That is liquid mass flow rate divided by the area of the cross section. Okay. So I will say L over A. What is G double prime? That would be G over A. So A gets cancelled here. Okay. So as long as you are looking at ratios of the mass velocity, it's also equivalent to the ratios of the mass flow rates. Okay. So L is 40, G is 23, square root of 2.8 over 63. So to save time, I have already calculated this. You should get something like 0.37. But 0.37 is not marked here in the x-axis, right? You got 0.1 somewhere here, and then you got 0.5. 0.37 should be somewhere in between. Okay. Do you know how to do interpolation in a log scale? Yes or no? Okay. I'll maybe towards the end of this problem, I'll talk about how to do interpolation. But I can locate that 0.37 is somewhere here using an interpolation technique. Okay, which I will discuss later on. Let's say I have known where exactly 0.437 is marked. So I go vertically here and then touch this line, and this basically comes out to be close to 0.8. So capacity factor Cp is 0.8. This corresponds to delta P by Z of 0.25 inches of H2O over feet and value of 0.37. Okay. So using these two information, I have found the capacity factor is 0.8. Okay. So now we know the definition of capacity factor. So this capacity factor Cp is defined as G double prime F power 0.5 nu to the power 0.05 okay, and this number is equal to 0.8. Okay, and if I go back to this to find the F parameter, okay, I go to this table and I'm looking at 1.5 inch ratcheting ring, and that gives me a value of 93. Okay, so F is 93 foot inverse, and the kinematic viscosity is given. All the rho G, rho L is also given, and we also know that G double prime is nothing but G over A. Okay, now I can solve for A. A is the only unknown in this equation now. So let's substitute this here. So you'll have G so A will be equal to G times F so G is 23, F is 93 power 0.5, and kinematic viscosity is 2. Densities are 2.8 and 63. And if you solve this, you will get an area of 22.1 feet squared. and then you equate this to the area, cross-sectional area of the column. And then if you solve for D from here, you get something like 5.3 feet. So what this means is, if I go back here, for the given flow rates of gas and liquid and a target pressure drop, if I use a column of diameter 5.3 feet, okay, that would give me the desired pressure drop to operate those desired liquid and gas flow rates. Okay, that's what this means. Now, if you were to do this problem for the another packing material, which is called the Paul rings, for the same size, you would have something like 40, right? Instead of 93 we used before, you would have 40, okay, and that would actually change the diameter little bit, okay. But later on I will show you that even though in the pressure drop calculation this material do not make such a big difference in the diameter, but they do affect the mass transfer rates, okay. We have not dealt with mass transfer yet. We are still talking about hydrodynamics or fluid mechanics of the packing and the flow. When it comes to mass transfer, these packing material, because they have a different interfacial area, the mass transfer rates affected by these can be very different. So it has to be hand in hand, that on one hand you have to look at pressure drop calculation and then measure your pressure drops, decide the column diameter and packing material. On the other hand, when you do mass transfer, you have to choose the right packing material to increase the mass transfer rates, okay. So you have to go handle both fluid mechanics problem as well as the mass transfer problem. Mass transfer problem we have not dealt with yet, okay. We are still looking at fluid mechanics. Okay, so now in many problems, you know, when you have this kind of a logarithmic scale and you will not get the actual data point that you want to be marked, so you have to know how to do interpolation to get the data, okay. So in this case I already showed 0.37 lies somewhere here, and then from there I mentioned it. So let me spend few minutes to say how do we do that, okay. Okay, so 0.1 is here, 0.5 is here, and then we want to locate where 0.37 lies, okay. So the way you do this is you write, so let's take 0.1 is somewhere here and 0.5 is somewhere here, and let's say this 0.37, I don't know where exactly it lies, but let's say it has to be somewhere in between, and I know it's going to be more closer to 0.5 than to 0.1, and let me say that this distance is A from this point, okay. I'm talking about now some linear distances. I've just taken that particular graph and I'm now looking at in a linear dimension what would be the length between 0.1 to 0.37. This is unknown to me right now, okay, but that's what I want to find out. And then this is B, okay, but A plus B would be the total length between 0.1 to 0.5 in a linear scale or a linear ruler, okay. So we say that the ln or log, you can use either way, let's use log of 0.5 minus log of x. So x is the location where I have to find, divided by log of x minus log of 0.1. This would be equal to log of 0.5 minus log x is actually b, and log x minus log 0.1 is actually a. So if I measure the segment length of b and a, okay, this relation should hold. Now I can also define a fractional, so this is a total distance a plus b, but I can define something called the fractional distance f as a by a plus b. So F tells me if I have this distance, total distance between 0.1 to 0.5 is 1 unit, what fraction would this point x be in this line is what this F means here. Okay, this is basically a fractional distance from the starting point. Okay, so from here I can show B by A will be nothing but 1 by F minus 1. Okay, so these are can be easily shown. So I will substitute this here, log 0.5 minus log x by log x minus log 0.1 is equal to 1 by F minus 1. So this interpolation formula can be used to locate any point x as long as x lies between 0.1 to 0.5 in this case. Okay, so and then substitute for x as 0.37, and then if you solve for this, you will get F is equal to something like 0.81. It means that this point 0.37 will lie at a distance of 81% of the total length between 0.1 to 0.5. So what you can do here, you take a ruler and you measure the distance, a linear scale ruler, you measure the distance from 0.1 to 0.5. Okay, so when I did this, this total length was A plus B was something like 4.1 centimeter. That's a total length between A and A to B. This is arbitrary, it depends on how much I zoomed in, but that won't change, okay, because we are working with the fractional distance. So in this particular figure, I measured the distance in a linear scale between 0.1 to 0.5. That total length is 4.1 centimeter. The 0.37 will lie at a distance of 0.81 of 4.1. Okay, so this A here will be 0.81 times 4.1. This is something like 3.33 centimeter. Okay, so I take a ruler here. From here I go to 3.33 centimeter, and that's where my point is. Okay, so having located this point, now I can go to the corresponding pressure drop and then calculate. Okay, same thing you do in a linear interpolation, we are doing the logarithmic interpolation. The only difference is instead of using the variable, we are taking the logarithmic of the variable. So that's a difference. Okay, otherwise this interpolation should be something you would have done. Whatever you have done in linear interpolation, you can do the same thing for logarithmic, provided that you change the variable into logarithmic scale. You can see that this is basically a sulfur dioxide used to be removed from a gas with the characteristic of air, okay, by scrubbing with an aqueous ammonium salt solution in a tower packed with 25 mm ceramic interlac saddles. The gas entering at the flow rate of 0.8 meter cube per second. The gas flow rate now is given in the volumetric scale, and the corresponding temperature pressures are given. And the gas contains 7% of SO2, which is to be nearly completely removed. The washing solution will enter at a flow rate of 3.8 kg per second. So liquid flow rate, mass flow rate is given, and as a density is also given. Viscosity is also given. Choose a suitable tower diameter. Okay, so this problem is exactly same as the previous problem, but only difference is they have not given all the units in the English units of our choice, but some are given in English units, some are given in SI units, so we have to play with it. Secondly, they did not mention about the pressure drop, target pressure drop. Okay, but as I said, we can only do it if the target pressure is mentioned. When such problems are there, you could say something like 50% of the pressure drop corresponding to flooding can be used, or maybe 80%, that's your choice. Okay, I did a problem where I used 50% of the flooding pressure, which is 0.5 inches of H2O per feet. Based on that, you can calculate. And also you can see that the density of the gas is not mentioned, but you know that the volumetric flow rate is given, temperature pressures are given. You can use the ideal gas law to get the density. Okay, and only the volumetric flow rate is given. You should be able to convert into molar flow rate, and then using the average molecular weight of the gas, you should be able to get mass flow rate also. Okay, so everything that you need are here, but not directly. Okay, so I will post this problem in Moodle, try to solve it. Maybe a few days before the quiz, I will probably send you the solutions also. But I insist that you try on your own. And the example that we have done here should be directly related to that. Okay, so you can see that the packing material is also different. It's given in inches. It's given in 25 mm, but we know 25 mm is close to 1 inch. Okay, and the material is interlac sawdulls. So you go here to this table. The interlac sawdulls are here, and 1 inch is here. So you'll be looking at an F parameter of about 92. Okay, and this particular table is taken from the text book Kussler, not the Treball. Treball has a different sets of units, so I didn't use it. So this comes from Kussler. I don't have the page number, but this should be I think chapter 6, I think. Okay, I'll just double check this later. Okay, so that's it for today.